What's up, guys? So today we are going to talk about glycosides and glycosidic bonds. So a glycoside is a very specific acetal. It's going to be an acetal formed from the reaction of an alcohol with a cyclic monosaccharide. So remember, cyclic monosaccharides are hemiacetals. So we have everything we need for this reaction. And this acetal linkage that we're going to form between our cyclic monosaccharide residue and our alcohol residue is what's called a glycosidic bond. Okay, let's try an example. So go ahead and pause this video and draw the product for this reaction. And then I want you to identify the acetal carbon and identify the glycosidic bond. Okay, let's see what you came up with. So this is a double replacement reaction where the hydroxy group attached to our hemiacetal carbon and the hydrogen attached to the oxygen of our alcohol are going to join together to form water, and then everything else is going to come together to form an acetal. And the glycosidic bond is going to be this bond right here between our acetal carbon and the new OC group. Okay, so let's do another one. So let's form another glycosidic bond here. But this time, both the hemiacetal and the alcohol are monosaccharides. So go ahead and pause this video and see what you can come up with. Okay, let's see what you got. So once again, this is a double replacement reaction. So we're going to take the hydroxy group attached to the hemiacetal carbon, and it doesn't matter which sugar you pick to be the hemiacetal donor, so I'm just going to pick the one on the left. And then I'm going to take the hydrogen attached to the oxygen on one of the hydroxy groups of the other sugar. And once again, unless I specifically tell you which one to use, it doesn't matter which one you choose. So those are going to come together to form water. And then we're going to connect everything else together to form an acetal. And so this acetal that we formed here is known as a disaccharide. So individual disaccharides are differentiated not only by the type of monosaccharide residues they're made from, but also the type of glycosidic bonds used to connect them. So to describe a disaccharide, you have to tell me both the type of residues that make it up, but also the type of glycosidic bond. So how do we name glycosidic bonds? So we're going to start by numbering the carbon atoms on both monosaccharide residues. So at this point, I want you to pause this video and go ahead and number both of the monosaccharide residues on this screen individually. Okay, your numbering should look like this, where the hemiacetal carbon or the acetal carbon, depending on which residue you're looking at, gets the lowest number possible. And speaking of that, now you need to identify which residue is the hemiacetal donor. So you kind of got to reverse engineer an acetal synthesis reaction. So we need both a hemiacetal and an alcohol to form an acetal. So which one of these residues acted as the hemiacetal and which one acted as the alcohol? So the residue that contains the acetal carbon is going to be our hemiacetal donor, and that means the other residue has to be our alcohol donor. Okay, next we need to determine the anomer of the hemiacetal donor. So look at your anomeric carbon and let me know if the oxygen is pointing up or pointing down. So since the oxygen attached to our anomeric carbon is pointing down, our hemiacetal donor is the alpha anomer. And then we're going to draw an arrow showing how the residues are connected. So we're going to take the anomeric carbon on the hemiacetal donor and draw an arrow pointing to the hydroxy carrying carbon on the alcohol donor. And then we're going to finish it off by placing the anomer type in front of the arrow. So the type of glycosidic bond connecting this disaccharide together would be an alpha 1,4. So alpha because our hemiacetal donor is in the alpha anomeric state, and our linkage goes from carbon number 1 on the hemiacetal donor to carbon number 4 on the alcohol donor. Okay, let's try an example. So go ahead and pause this video and see if you can tell me what type of glycosidic bond we have in the disaccharide below. Okay, so I'm going to start by numbering the carbons on each sugar residue individually. And then I'm going to identify my hemiacetal donor. So the residue on the left, since it contains the acetal carbon, it must be the hemiacetal donor. And so that means the residue on the right has to be our alcohol donor. So looking at our anomeric carbon on our hemiacetal donor, the oxygen is pointing up, so this is a beta anomer. And then we're going to draw an arrow showing that our glycosidic bond is connecting carbon 1 on our hemiacetal donor to carbon 4 on our alcohol donor. So this disaccharide contains a beta 1,4 linkage. Okay, let's try one that's a little bit different. This one's kind of tricky. So I want you to pause this video and see if you can tell me what type of glycosidic bond connects our fructose residue and our glucose residue in the disaccharide sucrose. Okay, so the sugar residues are already numbered for you. So the next step is to ask which monosaccharide is donating the hemiacetal. So which monosaccharide has an acetal carbon, has that CO-COC linkage? Well, the answer is both of them. They both have a CO-COC linkage. They both have acetal carbons. So this is a glycosidic bond that's been formed between two hemiacetals. So that means we need to know the anomeric notation for both of these residues, since they're both donating a hemiacetal. So let's look at our anomeric carbon on our top residue, our glucose. So the oxygen attached to the anomeric carbon is pointing down. So glucose is the alpha anomer. And then we have the opposite on our fructose residue at the bottom. The oxygen attached to the anomeric carbon there is pointing up, so it is in the beta conformation. So how do we write this when we have two hemiacetal donors and no alcohol donors? So since we have both an alpha anomer and a beta anomer, we have to list both. So alpha, comma, beta. And our bond is connecting carbon 1 on the alpha anomer to carbon 2 on the beta anomer. And since they're both hemiacetal donors, we're going to finish it off with a double arrow.